2's complement is a mathematical operation on binary numbers, as well as a binary sign number representation based on this operation. Its wide use in computing makes it the most important example of a radix complement. The 2's complement of an n-bit number is defined as the complement with respect to 2n. In other words, it is the result of subtracting the number from 2n, which in binary is 1 followed by n zeros. This is also equivalent to taking the 1's complement and then adding 1, since the sum of a number and its 1's complement is all 1 bits. The 2's complement of a number behaves like the negative of the original number in most arithmetic, and positive and negative numbers can coexist in a natural way. In 2's complement representation, positive numbers are simply represented as themselves, and negative numbers are represented by the 2's complement of their absolute value. Two tables on the right provide examples for now equals 3 and now equals 8. In general, negation is performed by taking the 2's complement. This system is the most common method of representing signed integers on computers. An n-bit 2's complement numeral system can represent every integer in the range a2 nar 1 to plus 2 nar 1 or 1, while 1's complement can only represent integers in the range a2 nar 1 or 1 to plus 2 nar 1 or 1. The 2's complement system has the advantage that the fundamental arithmetic operations of addition, subtraction, and multiplication are identical to those for unsigned binary numbers. This property makes the system both simpler to implement and capable of easily handling higher precision arithmetic. Also, 0 has only a single representation, obviating the subtleties associated with -0, which exists in one's complement systems. Potential ambiguities of terminology: one should be cautious when using the term 2's complement, as it can mean either a number format or a mathematical operator. For example, 0111 represents decimal 7 in 2's complement notation, but the 2's complement of 7 in a 4-bit register is actually the 1001-bit string, which is the 2's complement representation of a 7. The statement convert x to 2's complement may be ambiguous, since it could describe either the process of representing x in 2's complement notation without changing its value, or the calculation of the 2's complement, which is the arithmetic negative of x if 2's complement representation is used. Converting from 2's complement representation, a 2's complement number system encodes positive and negative numbers in a binary number representation. The weight of each bit is a power of 2, except for the most significant bit, whose weight is the negative of the corresponding power of 2. The value EW of an n-bit integer is given by the following formula. The most significant bit determines the sign of the number and is sometimes called the sign bit. Unlike in sign and magnitude representation, the sign bit also has the weight a2 nar 1, shown above. Using n bits, all integers from a2 nar 1 to 2 nar 1 or 1 can be represented. Converting to 2's complement representation, in 2's complement notation, a non-negative number is represented by its ordinary binary representation. In this case, the most significant bit is 0. Though, the range of numbers represented is not the same as with unsigned binary numbers. For example, an 8-bit unsigned number can represent the value 0 to 255. However, a 2's complement 8-bit number can only represent positive integers from 0 to 127, because the rest of the bit combinations with the most significant bit as 1 represent the negative integers a 1 to a 128. The 2's complement operation is the additive inverse operation, so negative numbers are represented by the 2's complement of the absolute value. From the 1's complement, to get the 2's complement of a binary number, the bits are inverted, or flipped, by using the bitewise NOT operation. The value of 1 is then added to the resulting value, ignoring the overflow which occurs when taking the 2's complement of 0. For example, using 1 byte, the decimal number 5 is represented by 000001012, the most significant bit is 0, so the pattern represents a non-negative value. To convert to a 5 in 2's complement notation, the bits are inverted. 0 becomes 1, and 1 becomes 0, 11 11 10 10. At this point, the numeral is the 1's complement of the decimal value of 5. To obtain the 2's complement, 1 is added to the result, giving 11 11 10 11. The result is a signed binary number representing the decimal value of 5 in 2's complement form. The most significant bit is 1, so the value represented is negative. The 2's complement of a negative number is the corresponding positive value. For example, inverting the bits of a 5 gives 0000100, and adding 1 gives the final value 0000101. The 2's complement of 0 is 0, inverting gives all 1s, and adding 1 changes the 1s back to zeros. Furthermore, the 2's complement of the most negative number representable is itself. Hence, there appears to be an extra negative number. Subtraction from 2n, the sum of a number and its 1's complement is an n-bit word with all 1 bits, which is 2n(a1). Then adding a number to its 2's complement results in the n lowest bits set to 0 and the carry bit 1, where the latter has the weight 2n. Hence, in the unsigned binary arithmetic the value of 2's complement negative number x of a positive x satisfies the equality x equals 2n(ax). For example, to find the 4-bit representation of a 5, x equals 510, therefore x equals 01012, hence, with n equals 4, x equals 2n, ax equals 24, 510 equals 100,000, 20112 equals 10,112. The calculation can be done entirely in base 10, converting to base 2 at the end. X equals 2n, ax equals 24, 510 equals 1110 equals 10,112. Working from LSB towards MSB, a shortcut to manually convert a binary number into its 2's complement is to start at the least significant bit, and copy all the zeros until the first A1 is reached. Then copy theta 1, and flip all the remaining bits. This shortcut allows a person to convert a number to its 2's complement without first forming its 1's complement. For example, the 2's complement of 0011A1100 is 1100A0100, where the underlying digits were unchanged by the copying operation. In computer circuitry, this method is no faster than the complement and add 1 method. Both methods require working sequentially from right to left, propagating logic changes. The method of complementing and adding 1 can be sped up by a standard carry look-ahead adder circuit. The LSB towards MSB method can be sped up by a similar logic transformation. Sign extension. When turning a 2's complement number with a certain number of bits into 1 with more bits, the most significant bit must be repeated in all the extra bits. Some processors have instructions to do this in a single instruction. On other processors a conditional must be used followed with code to set the relevant bits or bytes. Similarly, when a 2's complement number is shifted to the right, the most significant bit, which contains magnitude and the sign information, must be maintained. However, when shifted to the left, a 0 is shifted in. These rules preserve the common semantics that left shifts multiply the number by 2 and right shifts divide the number by 2. Both shifting and doubling the precision are important for some multiplication algorithms. Note that unlike addition and subtraction, precision extension and right shifting are done differently for signed versus unsigned numbers. Most negative number, with only one exception, starting with any number in 2's complement representation, if all the bits are flipped and 1 added, the 2's complement representation of the negative of that number is obtained. Positive 12 becomes negative 12, positive 5 becomes negative 5, 0 becomes 0, plus overflow, etc. The 2's complement of the minimum number in the range will not have the desired effect of negating the number. For example, the 2's complement of a 128 in an 8-bit system results in the same binary number. This is because a positive value of 128 cannot be represented with an 8-bit signed binary numeral. This phenomenon is fundamentally about the mathematics of binary numbers, not the details of the representation as 2's complement. Mathematically, this is complementary to the fact that the negative of 0 is again 0. For a given number of bits k there is an even number of binary numbers 2k, taking negatives as a group action on binary numbers, and since the orbit of 0 has order 1, at least one other number must have an orbit of order 1 for the orders of the orbits to add up to the order of the set. Thus some other number must be invariant under taking negatives. Geometrically, one can view the k-bit binary numbers as the cyclic group, which can be visualized as a circle, and taking negatives as a reflection, which fixes the elements of order dividing 2, 0 and the opposite point, or visually the zenith and nadir. Note that this negative being the same number is detected as an overflow condition since there was a carry into but not out of the most significant bit. This can lead to unexpected bugs in that an unchecked implementation of absolute value could return a negative number in the case of the minimum negative. The ABS family of integer functions in C typically has this behavior. This is also true for Java. In this case it is for the developer to decide if there will be a check for the minimum negative value before the call of the function. The most negative number in 2's complement is sometimes called the weird number, because it is the only exception. Although the number is an exception, it is a valid number in regular 2's complement systems. All arithmetic operations work with it both as an operand and a result. Why it works: given a set of all possible n-bit values, we can assign the lower half to be the integers from 0 to inclusive and the upper half to be a 2 na euro a euro 1 to a 1 inclusive. The upper half can be used to represent negative integers from a 2 na euro a euro 1 to a 1 because, under addition modulo 2n, they behave the same way as those negative integers. That is to say that because I plus j mod 2 newtons equals I plus mod 2n, any value in the set a euro j plus car euro 2n k is an integer a euro can be used in place of a j. For example, with 8 bits, the unsigned bytes are 0 to 255. Subtracting 256 from the top half yields the signed bytes are 128 to a 1. The relationship to 2's complement is realized by noting that 256 equals 255 plus 1, and is the 1's complement of a x. Example, AA95 modulo 256 is equivalent to 161 since, a 95 plus 256, equals a 95 plus 255 plus 1, equals 255 a 95 plus 1, equals 160 plus 1. Equals 161. 11 11 11 11 255, 01 01 11 11 and 95, 10 10 0 0 0 160, plus 1 plus 1, 10 10 0 0 0 161. Fundamentally, the system represents negative integers by counting backward and wrapping around. The boundary between positive and negative numbers is arbitrary, but the de facto rule is that all negative numbers have a leftmost bit of 1. Therefore, the most positive 4-bit number is 0111 and the most negative is 1000. Because of the use of the leftmost bit as the sign bit, the absolute value of the most negative number is too large to represent. For example, an 8-bit number can only represent every integer from a 128 to 127 inclusive. Negating a 2's complement number is simple: invert all the bits and add 1 to the result. For example, negating 1111, we get 0000 plus A1 equals A1. Therefore, 1111 must represent a 1. The system is useful in simplifying the implementation of arithmetic on computer hardware. Adding 0011 A3 to 1111 A1, at first seems to give the incorrect answer of 10,010. However, the hardware can simply ignore the leftmost bit to give the correct answer of 0010 A2. Overflow checks still must exist to catch operations such as summing 0100 and 0100. The system therefore allows addition of negative operands without a subtraction circuit and a circuit that detects the sign of a number. Moreover, that addition circuit can also perform subtraction by taking the 2's complement of a number, which only requires an additional cycle or its own adder circuit. To perform this, the circuit merely pretends an extra leftmost bit of 1 exists. Arithmetic operations, addition, adding 2's complement numbers requires no special processing if the operands have opposite signs, the sign of the result is determined automatically. For example, adding 15 and a 5. 11,111 111, 000 11 11, plus 11 11 10 11, 1010. This process depends upon restricting to 8 bits of precision. A carry to the ninth most significant bit is ignored, resulting in the arithmetically correct result of 1010. The last 2 bits of the carry row contain vital information, whether the calculation resulted in an arithmetic overflow, a number too large for the binary system to represent. An overflow condition exists when these last 2 bits are different from one another. As mentioned above, the sign of the number is encoded in the MSB of the result. In other terms, if the left 2 carry bits are both ones or both zeros, the result is valid. If the left 2 carry bits are 10, or 01, a sign overflow has occurred. Conveniently, an XOR operation on these 2 bits can quickly determine if an overflow condition exists. As an example, consider the signed 4-bit addition of 7 and 3. 0111, 0111, plus 0011, 1010 invalid. In this case, the far left 2 carry bits are 01, which means there was a 2's complement addition overflow. That is, 10,102 equals 1010 is outside the permitted range of 8 to 7. In general, any 2 n-bit numbers may be added without overflow, by first sign extending both of them to nar plus a 1 bits, and then adding as above. The nar plus a 1 bits result is large enough to represent any possible sum, so overflow will never occur. It is then possible, if desired, to truncate the result back to n bits while preserving the value if and only if the discarded bit is a proper sign extension of the retained result bits. This provides another method of detecting overflow which is equivalent to the method of comparing the carry bits but which may be easier to implement in some situations, because it does not require access to the internals of the addition. Subtraction. Computers usually use the method of complements to implement subtraction. Using complements for subtraction is closely related to using complements for representing negative numbers, since the combination allows all signs of operands and results. Direct subtraction works with 2's complement numbers as well. Like addition, the advantage of using 2's complement is the elimination of examining the signs of the operands to determine if addition or subtraction is needed. For example, subtracting a 5 from 15 is really adding 5 to 15, but this is hidden by the 2's complement representation. 11,110 000, 11 11, 11 11 10 11, 000 10100. Overflow is detected the same way as for addition, by examining the 2 leftmost bits of the borrows. Overflow has occurred if they are different. Another example is a subtraction operation where the result is negative, 15 AAA 35 equals a 20. 11,100 000, 000 11 11, and 0010011, 11 10 1100. As for addition, overflow and subtraction may be avoided by first sign extending both inputs by an extra bit. Multiplication, the product of 2 n-bit numbers requires 2 n bits to contain all possible values, but the 2 MSB are always equal and carry the same information. This is like having 2 sign bits. Therefore, 2 n1 bits are enough to store the result. If the precision of the 2's complement operands is doubled before the multiplication, direct multiplication will provide the correct result. For example, take 6a, a5 equals a 30. First, the precision is extended from 4 bits to 8. Then the numbers are multiplied, discarding the bits beyond 8. 0000110, 11,111,011, 110, 1100, 00000, 110,000, 1,100,000, 11 million, x1000000, xx0000000, xx1110010. This is very inefficient. By doubling the precision ahead of time, all additions must be double precision and at least twice as many partial products are needed than for the more efficient algorithms actually implemented in computers. Some multiplication algorithms are designed for 2's complement, notably Booth's multiplication algorithm. Methods for multiplying sign magnitude numbers don't work with 2's complement numbers without adaptation. There isn't usually a problem when the multiplicand is negative. The issue is setting the initial bits of the product correctly when the multiplier is negative. Two methods for adapting algorithms to handle 2's complement numbers are common. First, check to see if the multiplier is negative. If so, negate both operands before multiplying. The multiplier will then be positive, so the algorithm will work. Because both operands are negated, the result will still have the correct sign. Subtract the partial product resulting from the MSB instead of adding it like the other partial products. This method requires the multiplicand sign bit to be extended by one position, being preserved during the shift-right actions. As an example of the second method, take the common add and shift algorithm for multiplication. Instead of shifting partial products to the left as is done with pencil and paper, the accumulated product is shifted right, into a second register that will eventually hold the least significant half of the product. Since the least significant bits are not changed once they are calculated, the additions can be single precision, accumulating in the register that will eventually hold the most significant half of the product. In the following example, again multiplying 6 by a 5. The two registers and the extended sign bit are separated by vertical bar. 00110, 1011, equals 001100000, 0011000, 010001000, 001001000, 001001000, 001001000, 111000100, 111100010, 11100010. Comparison. Comparison is often implemented with a dummy subtraction, where the flags in the computer's status register are checked, but the main result is ignored. The zero flag indicates if two values compared equal. If the exclusive or of the sign in overflow flags is 1, the subtraction result was less than 0, otherwise the result was 0 or greater. These checks are often implemented in computers in conditional branch instructions. Unsigned binary numbers can be ordered by a simple lexicographic ordering, where the bit value 0 is defined as less than the bit value 1. For 2's complement values, the meaning of the most significant bit is reversed. The following algorithm sets the result register to a 1 if A, B, to +1 if A, B, and to 0 if A and B are equal. Reversed comparison of sign bit, if A, N1, 0 and B, N1, 1N, R, equals +1, break, else if A, N1, 1 and B, N1, 0 then, R, equals -1, break, end. Comparison of remaining bits, for I equals N2. 0 do, if A, I, 0 and B, I, 1 N, R, equals -1, break, else if A, I, 1 and B, I, 0 then, R, equals +1, break, end, end. R, equals 0. 2's complement and two-adic numbers, in a classic Hackman published by the MIT AI Lab in 1972, Bill Gosper noted that whether or not a machine's internal representation was 2's complement could be determined by summing the successive powers of 2. In A Flight of Fancy, he noted that the result of doing this algebraically indicated that algebra is run on a machine which is 2's complement. Gosper's end conclusion is not necessarily meant to be taken seriously, and it is akin to a mathematical joke. The critical step is 110 equals 111 AAA1, that is, 2x equals AAA1, and thus A equals A. 111 A equals AAA1. This presupposes a method by which an infinite string of ones is considered a number, which requires an extension of the finite place value concepts in elementary arithmetic. It is meaningful either as part of a 2's complement notation for all integers, as a typical two-adic number, or even as one of the generalized sums defined for the divergent series of real numbers 1 plus 2 plus 4 plus 8 plus AAA. Digital arithmetic circuits, idealized to operate with infinite bit strings, produce two-adic addition and multiplication compatible with 2's complement representation. Continuity of binary arithmetical and bitewise operations in two-adic metric also has some use in cryptography. See also, division algorithm, including restoring and non-restoring division and 2's complement representations, offset binary, P-adic number, references. Further reading, Kiran, Israel. Computer Arithmetic Algorithms. A.K. Peters. ISBN A1-56881-160-8. Flores, Ivan. The Logic of Computer Arithmetic. Prentice Hall. External links, tutorial, 2's complement numbers, 2's complement array multiplier JavaScript simulator, JavaScript converter for 2's complement to decimal and vice versa.